There are different methods of computer-aided drug designing, and today we are going to learn important drug designing methods. Earlier, we mentioned about de novo method and Edmonds property prediction and hit identification, then lead identification stage, later lead optimization and how to reduce toxicity level and all those associated things. And along with that, we mentioned some important computational approaches like ADMET models like that. So today's video is about the molecular mechanics and molecular dynamics about the docking. So a term called molecular mechanics is very relevant in this case. So the term molecular mechanics refers to the use of Newtonian mechanics to model molecular systems. The potential energy of all systems in molecular mechanics is calculated using force fields. We will be using force fields. So molecular mechanics can be used to study small molecules as well as large biological systems or material assemblies with many thousands to millions of atoms. So all atomistic molecular mechanics methods have the following properties. Like each atom is simulated as a single particle. Each particle is assigned a radius, polarizability and a constant net charge. Then bonded interactions are treated as springs with an equilibrium distance equal to the experimental or calculated bond length. Then variation on this theme are possible. For example, many simulations have historically called a united atom representation in which methyl and methylene group were represented as a single particle. And large protein systems are commonly simulated using a bead model which assigns 2 to 4 particles per amino acid. Then functional form. Molecular mechanics potential energy function with continuum solvent. The following functional abstraction known as a potential function or force field calculates the molecular system's potential energy in a given conformation as a sum of individual energy terms, like E is equal to E covalent plus E non-covalent energy, potential energy. So the components of the covalent and non-covalent contributions are given by the following summations. E covalent is equal to E bond plus E angle plus E dihedral. All these E represent the potential energy, nothing else. Okay. So E non-covalent is equal to E electrostatic plus E van der Waals. The exact functional form of the potential functions or force field depends on the particular simulation program being used. Generally, the bond and angle terms are modeled as harmonic potentials centered around equilibrium. Bond length values derived from experiment or theoretical calculations of electronic structure performed with software which does ab initio type calculations such as Gaussian. So for accurate reproduction of vibrational spectra, the Morse potential can be used instead at computational cost. The dihedral and torsional terms typically have multiple minima and thus cannot be modeled as harmonic oscillators, though their specific functional form varies within the implementation. Then the non-bonded terms are much more computationally costly to calculate in full, since a typical atom is bonded to only a few of its neighbors, but interacts with every other atom in the molecule. Generally, a cutoff radius is used to speed up the calculation so that atom pairs whose distances are greater than the cutoff have a van der Waals interaction energy of 0. Then switching or scaling functions that modulate the apparent electrostatic energy are somewhat more accurate methods that multiply the calculated energy of a smoothly varying scaling factor from 0 to 1 at the outer and inner cutoff radii. So, other most sophisticated but computational intensive methods are known as particle mesh evolved PME and the multiple algorithm. Then areas of application, the prototypical molecular mechanics application is energy minimization. That is, the force field is used as an optimization criterion and the local minimum searched by an appropriate global energy optimization can be accomplished using annealing, the Metropolis algorithm and other Monte Carlo method. The main aim of optimization method is finding the lowest energy conformation of a molecule or identifying a set of low energy conformers that are in equilibrium with each other. The force field represents only the ephthalic component of free energy, and only this component is included during energy minimization. So molecular mechanics potential energy functions have been used to calculate binding constants, protein folding kinetics, protonation equilibria, active site coordination, and to design binding sites. So molecular mechanics and molecular dynamics are related but different. So main purpose of molecular dynamics is modeling of molecular motions, although it is also applied for optimization. For example, using simulated annealing. Molecular mechanics implements more static energy minimization methods to study the potential energy surfaces of different molecular systems. So molecular mechanics can also provide important dynamic parameters such as energy barriers between different conformers or steepness of a potential energy surface around a local minimum. So molecular mechanics and molecular dynamics are usually based on the same classical field, free fields, force fields. But molecular dynamics may also be used to quantum chemical method like DFT. Is also used to define a set of techniques in molecular modeling. So molecular mechanics methods are based on the following principles. Nuclei and electrons are lumped into atom-like particles. Atoms like particles are spherical and have a net charge. Interactions are based on springs and classical potentials. Interactions must be pre-assigned to specific set of atoms. Interactions determine the spatial distribution of atoms like particle and their energies. Anatomy of molecular mechanics force field. The mechanical molecular model considers atoms as spheres and bonds as springs. The mathematics of spring deformation can be used to describe the ability of bonds to stretch, bend, and twist. Although van der Waals attraction, steric repulsion, and electrostatic attraction or repulsion, these properties are easiest to describe mathematically when atoms are considered as spheres of characteristic radii. The object of molecular mechanics is to predict the energy associated with a given conformation of a molecule. However, molecular mechanics energies have no meaning as absolute quantities. Only differences in energy between two or more conformations have meaning. The simple molecular mechanics energy equation is given by energy is equal to stretching energy plus bending energy plus torsion energy plus non-bonded interaction energy. So different types of energies we mentioned. These equations together with the data required to describe the behavior of different kinds of atoms and bonds are called a force field. Many kinds of force fields have been developed. Some include additional energy terms that describe other kinds of deformations. Some force field account for coupling between bending and stretching in adjacent bonds in order to improve the accuracy of the mechanical model. Then stretching energy. The stretching energy equation is based on Hooke's law. Then bending energy is also like that, which is also based on Hooke's law. Then torsion energy in molecular mechanics is particularly used to correct the remaining energy terms rather than to represent a physical process. The torsional energy represents the amount of energy that must be added to or subtracted from the stretching energy or bending energy. Non-bonded interaction energy terms to make the total energy agree with experimental quantum mechanical calculations for a model dihedral angle. Then non-bonded energy. The non-bonded energy represents the pairwise sum of energies of all possible interaction non-bonded atoms, I and J. Then molecular dynamics. Molecular dynamics is a form of computational simulation in which atoms and molecules are allowed to interact for a period of time by approximation of known physics, giving a view of the motion of the atoms. Because molecular systems consist of a vast number of particles, it is impossible to find the properties of such complex systems analytically. Molecular dynamics probes the relationship between molecular structure, movement, and function. Molecular dynamics is a multidisciplinary method. Its law and theories stem from mathematics, physics, and chemistry, and it employs algorithms from computer science and information theory. So molecular dynamics is a specialized discipline of molecular modeling and computer simulation based on statistical mechanics. The main justification of the MD method, molecular dynamics method, is that statistical assemblage average is equal to time average of the system, known as the ergodic hypothesis. MD has also been termed statistical mechanics by numbers and Laplace vision of Newtonian mechanics of predicting the future by animating nature's forces and allowing insight into molecular motion on an atomic scale. Areas of application, different areas are there which work with the application of these principles. In chemistry and biophysics, the interaction between the particles is either described as a force field, classical MD, quantum mechanical model, or a mix between the two. In chemistry, MD serves as an important tool in protein structure determination and refinement using experimental tools such as X-ray crystallography and NMR. It has also been applied with limited success as a method of refining protein structure predictions. In physics, MD is used to examine the dynamics of atomic level phenomena that cannot be observed directly, such as thin film growth and ion subplantation. It is also used to examine the physical properties of nanotechnological devices that have not or cannot yet be created. In applied mathematics and theoretical physics, molecular dynamics is a part of the research realm of dynamical systems, ergodic theory, atomic, molecular, and optical physics, and statistical mechanics in general. MD can also be seen as a special case of the discrete element method, DEM, in which the particles have spherical shape with the size of their van der Waals radii. Theory of molecular dynamics. One of the principal tools in the theoretical study of biological molecules is the molecular dynamic simulation. The computational method calculates the time-dependent behavior of a molecular system. MD simulations have provided detailed information on the fluctuations and conformational changes of proteins and nucleic acids. These methods are now routinely used to investigate the structure, dynamics, and thermodynamics of biological molecules and their complexes. They are also used in the determination of structures from X-ray crystallography and from NMR experiments. Then biological molecules exhibits a wide range of timescales over which specific process occurs. For example, local motions, atomic fluctuations, side chain motions, loop motions, rigid body motions, helix motions, domain motions, then submit motions, large scale motions, helix coil transition, dissociation or association, folding and unfolding. And classical molecular dynamics are used for energy minimization and dynamic simulation of proteins, nucleic acids, and lipids in vacuum, solution, or crystal environments. And uses of molecular dynamics and simulations. Molecular dynamics simulations permit the study of complex dynamic processes that occurs in molecular biological systems. These include, for example, protein stability, conformational changes, protein folding, molecular recognition, proteins, DNA membranes complexes, joint transport in biological systems, and provide the mean to carry out the following studies like drug design, structural determination with X-ray and NMR methods.